A warm welcome and very good evening to all dear participants. The resource person of today's session, Dr. Atanu Bhattacharya sir. Today, we are having our lecture on computation and application of correlation. Now, I would like to introduce today's resource person of the session, Dr. Atanu sir. Sir is currently working as a lecturer in medical statistics at the University of Leicester, United Kingdom. He previously served as an assistant professor at the section of Biostatics, Center for Cancer Epidemiology, Tata Memorial Centre, India, and the Malabar Cancer Centre, Kerala, India. He completed his PhD at Guwahati University, Assam, on Bayesian statistical inference. He is an elected member of the International Biometric Society Indian region. Sir has published over 250 research articles in various peer-reviewed journals. Now, I would like to invite Sir to kindly lead today's session. Please, Sir, welcome, Sir.
Thanks, Amit. I think I'm audible to you.
Yes, Sir.
Thanks. I'm pleasure. It's my pleasure to be associated with the presentations and today's talk about the computation and applications of correlations. So yeah, so currently, before to move to the UK, I worked at Tata Memorial Centers, Mumbai. So mostly I worked on clinical research, clinical trials related to oncology, and there I developed so many statistical methods as well as applied in the clinical trial. And right now I'm working with the big data, real world primary care data unit here in the UK. So, as the topic given to me by Shubham, that about the computation and application of correlations. So, going to say more about this, the preliminary part about the computation and applications of the computation correlations. But mm, in in today's advanced statistics as well, this fundamental application is quite relevant, and we many places we do apply these correlations coefficients. In fact, in different data analysis, and as I mentioned, it's quite a fundamental tool to be used in any advanced statistical technique, as well as these fundamentals or conventional statistical methodology. So in that context, I will present something about this importance of the correlations coefficients and how to make it and what's that requirement and what are the misuse of the correlations coefficient would be there. I think that would be quite sufficient to present the thing because mm, nowadays having the software, having Google and so many AI tools are available. So there are people don't need to be worried about how to apply those things. So that kind of things are already over. But challenge is still we are having that whatever we are applying, it's correctly applying or not. And after applying whatever the result we are getting, this is correctly making sense and interpretable or not. So these are the two things need to be concerned. So whatever we are applying, correctly applying or not, and after applications of the correlations coefficients with statistical tools and packages, the results we are going to get, it is interpretable and we are making correct interpretation or not. So that's the current scenario of this challenge. Earlier days, people used to have that third challenge. I think that slowly that challenge is going to have a, that is this how to apply and means to basically to hand somebody's hold somebody hand and then show that this is the way it should be done. But that because of the YouTube and other so many platforms are available, if somebody is really curious to apply the correlations coefficients in the data, so that can be done. So basically so many n number of opportunities are there so people can learn. So I'm not going into details on how to calculate, but where to, and once we are apply how the things are going on. So mainly I focused on that part here. So the purpose of this presentation is to provide an overview of the computation and application of the correlations, particularly in the medical research or Ayurvedic research. I don't find any difference in between medical research and Ayurvedic research in terms of the applications of the correlations, coefficients, correlations. So I'm trying to make that basic fundamentals of the correlations, how to calculate the correlations, and what are the different types of correlations, and simultaneously we'll discuss some common applications and possibilities in other future applications where correlations could serve a better tool, and then again for in any advanced computation or complex analysis it could be used as a fundamental statistical tool than anything else. So that's the point. So, what is the correlations? Correlation is statistical methods that is used to measure the relationship between the two or more variables. The two and more variables could be the variables, as I said, that the variables could be, let's say, age with BMI. So you want to see weight with BMI. You want to see. So one variable should be one parameters of the representations of the human features. Another variable, another parameter should be another features representation. So now we want to make this relations between these, that kind of relations, meaning that the relations between the two features or two variables, and that been obtained by that numerical relation. I would say, I would not say that any emotional relation or any subjective relations. Typically the numerical relation, how they are standing with each other. So for that the correlations stand, and the relationship, again, that I would like to stress that the relationship is typically these numerical correlations between two variables. Now there are some value, limit value, as I mentioned, that it is a numerical correlations that mean or numerical relationship between these two variables. So there must be some maximum and minimum limit of these parameters, and these parameters, the correlations parameters, precisely the parameters are called as the correlation coefficients, and many books present these correlations coefficients as rho, and this stand from -1 to +1. So, and where the -1 indicate that it's a perfectly negative correlation, and +1 believe that it's a perfectly positive correlations, and while the 0 is between stand between -1 to +1, 0 indicate that there is not any correlations between these two parameters or features. I'm keep on changing the terminology, parameter, features, variable, but they are same. So um, in this context, parameter, features, variable, these are the same. So nothing to be worried about that. But yeah, so -1 said that one if one parameter is increasing, so another will be decreasing, numerically decreasing. +1 says that one parameter is increasing, so another parameter will also increase, numerically increasing. And 0 means if there is not any numerical relationship between these two parameters, so they are hardly bothered to each other. If one parameter increases, then other parameters makes might be that they that not increase or decrease, nothing. There is not any directional changes in another parameter. So that's that stand as 0, indicating as a no relation between these two parameters. So the type of correlations, there are different type of correlations that I say, that is a positive, negative, and 0. So 0 means there is no relation, so that is standing as a correlations. Negative, if it is going from 0 to -1. So as I mentioned, that -1 is this minimal limit. So any value between 0 to -1, so -3, -0.3, -0.4 to up to -1. So any value between these would be suggested as a negative correlations. Any value between 0 to +1, so zero point 0.2, zero point 0.3, like up to 1, would be defined as a positive correlation. So these are that positive correlations. So these are the uh, two limit value on the x-axis. We say like that, from 0 to 1 as a positive, from 0 to -1 as a negative, and if it is exactly 0, um, it is no relations or 0 relations. But that's quite straightforward or thumb rule to make that statement. But in reality, we hardly get exactly plus positive or +1 correlations coefficients, neither -1 negative correlations coefficients or 0. So always we get towards positive. Towards means towards 1 correlations coefficients, towards minus 1 correlation coefficients. Let's say minus 0.93. So that would be the negative towards negative maximum minimal value. And similarly 0.93, 0.94, that would be this towards plus 1. So that will be the positive. And if it is a 0, that's mean or near to 0, 0.022, 0.03, 0.04, all these stuffs are can be compensated near to 0 positive. I will show that how these categorizations can be done of the correlation threshold in value in later slides. But yeah, so positive, I already mentioned and that. So and in layman terms, in English language, if we want to say when the values to variable increase or decrease together, when one increase, another decrease, or another increase, first one decrease, there will be negative correlations, and zero when there is no relationship between these. So there is no hardly matter if one increase, then another will not decrease or increase. It's not going to change anything for the another variable, and that would be called as a zero correlations. There are the some fundamentals equations formula to Pearson correlations. So I'm not going much more details about the Pearson correlations. Fundamentally, if you say about the correlations coefficients, by default we understand that correlation is nothing but the Pearson correlations coefficients. And in that sense, it stands with two parameters like or two variable as I mentioned that x and y. So it's a multiplication of these two parameter numeric value, and thereafter we subtract that x value, and thereafter we multiply with subtract the multiplication of x and y value divided by n, and again make the square root of x square minus x square minus x, thereafter enter square divided by n, and this line. So this is the Pearson correlations coefficients formula. Some books suggest as is R, somebody says it's a rho, somebody says as the Pearson. So these are the all same. So let's say it's very useful because as we mentioned that we are working for the medical research or the Ayurvedic research of human bodies. So always we try to find out some relations or example parameters from these from our body or some human to understand the human features. So that fundamentals or primary parameter, let's say height and weight. So let's say this is the height value and this is the weight value. And this height value is being presented as in inches 62, 65, like up to 116. And weight value is also represented by pounds, like 90, 100, and all this stuff. Then if we calculate, so as we if we calculate the correlations, Pearson's correlations coefficient between these two values, then it will become as a 0.994. So it suggests that strong positive correlations between height and weight does mean when the body's weight increases, body height will also increase, or when the body height increases, body weight will also increase. Look here, we are taking this only the numerical value for body weight and the same individual. So persons, if wants to make the data, this is the person's first person 62 is his height, and the same person's a weight is 90. First here it is 90. The first person's 90 is 90 pound is his weight. Similarly, second person's height is 65 5 inches, but his weight is 100 pound. So that should be this data should be presented in such a way then you can make that. It should not be in any diversing, or that should be always maintained properly. And another thing is that sometimes in common routine data analysis, we find out in the data set, let's say we are having 100 individuals, and out of that 90 individuals height is present and 10 individuals height is not available, or somehow due to the data entry mistakes or due to this non-availability of their data, people didn't give the consent, we didn't measure the value, so that values were not being measured. So out of 100, let's say 10 individuals values are not present. Whereas again, for the weight also, out of this 100 individual, let's say for 85 individuals values are present and 15 individuals values are not present. Now it could happen that 10 individuals their height was not present, Similarly, 15 individuals, out of that 15 individuals, 10 also not having weight. So there is a common area, common people, that 10 people neither having height available, not having weight available. So once you are talking about preparing the correlation coefficients, it would consider only 85 individuals. Those are having height and weight, both the things. Um, it's a good thing that if you are having both the value, both the stain individual having no information from both the side, then obviously it will become down to 90 exactly. But still, if 5 individuals more that is not available the weight value, it will come down to 85 in place of 90. It might happen that 10 individuals from this 100 from 100 having no height, and 15 individuals from the again 100 individuals having no weight value. So it might happen that there is not any common people, those are having neither height nor weight value. That might possible. In that case, total number of people having either height value or weight value, those are both of one of the things are missing. That is going to be 10 plus 15, that is 25. So in that sense, 75 out of 100 will be having correlation coefficients to calculate while we are going to make then overall from 90 or 100. So once that need to be kept in mind. So software don't say that, but once you're calculating that stuffs, it need to be kept in mind that if your data is not fully fully captured for all individuals, each for all individuals parameters have been measured, then we are not going to get the value here. So that's the one point need to be noticed. There is some alternative measures of Pearson correlations is there. That is also strong correlations coefficients, and I would say that fundamentally there is a two types of correlations coefficients. And one is the Pearson correlations and the Spearman correlations. And Spearman rank correlations stand basically again range is again it's also having -1 to +1, and it stands with 0 correlations coefficients. But the formula to calculate this Spearman rank correlation is a little different, and it is basically used the order statistics. So it's rank that's variable corresponding value of the parameter in such a way first, and ascending order or descending order variable values thereafter it calculates the Spearman correlation. So for example, the same example where we are having height and weight example. So let's say that height rank, so it will rank as the first individual will be ordered as first as a 39. So this is the minimal height of the rank, and I'm sorry, it should be ranking in 39 should be come to here. So and thereafter 40, 41, 42. So all this rank will be ascending in such a way that what should be the ranking for that first parameter. Similarly, weight ranking for the second parameter will be there, and thereafter we can calculate that correlations coefficients between height and weight parameters. So by the Spearman correlations coefficients, this is the way it happens like that. Applications of correlations in medical research is commonly used in risk factors to identify the risk factor for disease, to predict the disease outcomes, to evaluate the effectiveness of treatments, assess the reliability of the diagnostic test, investigate the relationship between these environmental factors and health outcome. And we'll go into the next slides with about this, some fundamental applications with these correlations coefficients. So basically, as a preliminary steps, we use the correlations coefficients to identify or explore the data that is these two parameters, two features are really linked with each other or not. For that, we commonly use the correlations coefficients as a fundamental parameters, tool, statistical tool to explore the data. It can be used risk factor for disease by examining the relationship between the potential risk factor and disease incidence. For example, A study might examine the correlation between smoking and lung cancer incidence. A strong positive correlation between smoking and lung cancer would suggest that smoking is a significant risk factor for a disease. Yes, cancer, lung cancer disease. But yeah, so how you will get that what the number of now question is that how you will prepare the data. So if you randomly select some lung cancer patients, and let's say hypothetically, I'm trying to explain. Let's say we go to a hospital because getting lung cancer patient in a community is not so easy. So you have to be rely on some cancer hospitals or some oncology institute where you can get easily the correlations coefficient lung cancer patients. So once that is there you can find out how many of them are having, or how what is the magnitude of the smokers, how many cigarettes they used to smoke per day. That kind of values you can get, and simultaneously you can go in the community and find out this if person is normal, having no lung related issue, lungs perfectly all right, and from them you can find out any of them are taking any cigarette. If yes, then how many of them are taking cigarette, and you will see obviously the majority will not having any cigarette smoker. So that's the way. But one thing is that I'm trying to trace much more example here is the number of cigarette than number of cigarette smoker or not, because it is very easy to make the data or ask the individual you are a smoker or not. But getting the data as a how many cigarette a person take, it is quite it's not so easy to answer. And obviously those don't have the cigarette smoker, don't smoke, obviously they are going to say it's a zero. The reason behind that I'm trying to make as a how many numbers of cigarette, because mm, if you want to apply really the correlations coefficients, the both side parameter need to be continuous variable. Like you have seen that height and weight, both of them are continuous variable. Well, you're talking about the smoking scenario with lung cancer. Obviously, lung cancer would also be these parameters or severity level of lung cancer, and as well as that and number of cigarette people have been taken. Otherwise, you can't make it as a continuous variable, because lung cigarette smoking or not, that is also a binary variable. Lung cancer have or not, that also binary variable. So in that context, correlations coefficients would not give you the direct impact. But if you really want to have the lung cancer severity and or in a lung severity status, as well as the cigarettes taking number of cigarettes taking proportions value, then that correlations coefficient could be very much useful in that context. Now, once you are having the correlations coefficient, then we can use also, it can be used to predict the disease outcome. So correlations can be used to predict disease outcome by some examining the relationship between the disease severity and other factor. For example, a straightforward methods could be a study might examine the correlation between blood glucose level and the progression of the diabetes retinopathy. So blood glucose level is typically a continuous variable, and this progressions of diabetes is also a it's a typically continuous variable. So that could be merged very nicely, and thereafter we can make say that this is the predictor of the disease outcome. A strong positive correlation between blood glucose level and disease progression would suggest that controlling the blood glucose is important for preventing or slowing the progressions of the disease. Evaluating the effectiveness of treatment, correlations can be used to evaluate the effectiveness of the treatment outcome by examining the relationship between the treatment and disease outcome. For example, the study might examine the correlations between a new drug and possible reduction of the symptoms of the particular disease, like pain relief disease, pain relief drugs, and we have to find out that how the pain has been relieved. Obviously, it is not going away, but level of scaling of the pain is reduced or not. A strong positive correlation between the drug and symptoms reducing would suggest that the drug is effective in treatment. So obviously here in that context, evaluating while you are taking, so if you're saying that pain pain score being measured from, let's say, from 0 to 10, and drug doses being measured from, let's say, 50 mg, 100 mg, 150 mg, and 200 mg. So these are the two part. One is drug taken, on amount of drug taken, and in another part the pain score of an individual. So now, once you are giving 50 mg drugs to some individuals and see after end of 2 weeks, the pain score was before 2 weeks, pain score was, let's say, mean pain score was around 8 or 9. After 2 weeks, it is come down to 4 or 5. If you get that 100 mg, then again the same scenario. Before 2 weeks, before taking the drug of 100 mg, pain score was around 8 or 9, but it is come down to, let's say, 3 to 4, and simultaneously for 150 and 200. So basically doses are also changing here, but here increasing doses but reducing pain score. That is quite expected, but that is because if you increase the dose level of the painkiller, so obviously the pain will be much more lesser than that. So in that case, the question is that is it a positive correlations or negative correlations? So definitely the negative correlations, because numerical value, while the drug doses numerical values keep on increasing from 50 to 100, from 150 then 200 mg, but the pain score values keep on decreasing from mean value from 8 9 to, let's say, 7 8, thereafter 6 4 5, and thereafter 2 3. So here the numerical value of pain score is keep on declining, where you are increasing the drug doses value. So this is typical example of the negative correlations coefficients of negative correlations, and that is always expected. In other way around, let's say another example, you can take that hemoglobin increasing, because there are some iron folic acid tablet people to use and try to incline their hemoglobin level. So in that case, if you increase the iron folic acid volume, number of tablet per day intake, or the mg level or quantity of the tablet per day for an individuals, so obviously the numeric value, once you are giving much more or more frequent iron folic acid value to an individual, their blood hemoglobin level will also increase, and that is quite expected. In that sense, we should say that, that they are positively correlated with each other. So one's value is increasing, another value is also increasing, and they are positively, and that is as per as expected. So it's depend on, the moral of the story is that it's depend that in some extent, some scenario we believe that negative correlations coefficient would serve us better, and in some way we think that the positive correlations coefficients would serve us better. It's depend on the scenario. Okay. Assessing the reliability of the diagnostic test, correlation can be used to assess the reliability of diagnostic test, but examining the relationship between test result and actual presence and absence of the disease. For example, a study might be examining the correlations between the results of a mammography and actual breast presence of the absence of breast cancer. So, a strong positive correlations between the mammography results and presence of the breast cancer suggests that mammogram is a reliable diagnostic test for the disease. Now, I would like to put much more attention in that. This is fundamentally for concept clearance, that is fine. We can use this mammography data and breast cancer outcome for that. But there is an advancement of this correlation coefficient that is mostly called as sensitivity analysis or specificity analysis, to find out the true positive, true negative, false positive, false negative. That entirely different parts together. But yeah, these are fundamental applications. So basically the fundamental things are based on the correlations coefficients. So yeah, so if this, in terms of the simplest term, if you try to say, if the strong positive correlations exist between mammography result and presence of breast cancer, it suggests that the mammography is a reliable diagnostic test for the disease. Investigating the relationship between environmental factor and health outcome. Investigate the relationship between the environmental factor and the health outcome by examining the relationship between the exposure and environmental factors. Similarly, the study might examine the correlation between the air pollution and respiratory disease or illness. Strong correlations between air respiratory disease suggests that the air pollution is significant environment risk factor for the disease. Now I'd like to put some note on that limitations of the correlation or correlations coefficient in medical research. It's quite useful tool in medical research, but has some limitations. Obviously, it does not put the causations. A strong correlations between two variables mean that one variable causes to other variable. It can influence by the confounding variable as well. Confounding variables are the factor that affect both the independent, but means both the variable, both the features being affected by these confounding factors. Then it makes no sense to apply the correlations coefficient and establish the fact that one variable is related to other variable, and it's been quite difficult to determine the true relationship between these two variables. In that case, correlation is not always appropriate. It sometimes assume a higher relationship between the two variables, but it might not be in the always, let's say. So I would not suggest to take that correlations coefficient as a predicted variable. So prediction purpose, don't try to use the correlations coefficient. There are so many other applications of statistical methods are there. Those can be choose to find out the you know causal effect, and that strong relation or proper relations between these two variables. But as a fundamental explorations or fundamental stacks, definitely correlations give us that primary way of looking the data figure. And now let's say we are having huge data sets. Let's say we are having 10,000 parameters on individuals genomic parameter, and you never know which parameters are contributing to another parameters or not, or parameters are really interlinked with each other or not. In that context, definitely the preliminary data explorations with correlations help us a lot to figure it out or filter it out, that relevant variable from the data sets. Based on that, we can go much more on statistical modeling and other stuff. But as a preliminary statistical tools, obviously correlations coefficients help us a lot to understand that relationship between these two variables, how they are linked. Using correlations in conjunction with other statistical methods to overcome the limitations of the correlation, it is important to use that conjunction with these other statistical methods. For example, regression analysis can be used to determine the directions and strength of the relations between the two variables, like ANOVA chi-square test can be used as an analysis data and draw accurate conclusions of that. So there are so many parameters, but ANOVA fundamental, if you say the fundamental of that ANOVA also depend on it's basically depend on the regressions. It's extension of the regression coefficients, and regression coefficients will be calculated based on the correlations coefficients, but that is a different story. But yeah, so I would say that once you are trying to find out the causality relations between the two variables, it is better to go with the ANOVA or some chi-square test or some other statistical methods rather than only jump or stand with the correlations coefficients. That's the point to be noted. There are some common mistakes the researchers make always to make the correlations coefficients. That is a fundamental to the assumptions mistakes. So it's always assumed that one is causing. So no, it can't give you the entire pictures of the causal effect relationship between the two variables. I repeat, it never give you that causal effect relationship between the two variables. Correlations coefficient does not prove causation. It is important to use other method to determine the correlations. Using the wrong type of correlations, it is important to use the appropriate type of correlations for the data to be analyzed, and including confounding variables. Correlations can be influenced by confounding variables, and that will be taken care properly, tackled properly while you are making the value for the correlations coefficients. Common misconception. There are some misconception. Correlation is always positive. No, that's never happened. It could be 0 and -1 as well, that I mentioned earlier. It could be is always strong. Correlation can range between -2 plus 0 indicating no correlations, and correlation implies causations. Correlation does not prove causations. Correlation and causations are often confused, but they are not same thing. Correlations is the strength and direction of the relationship between the two variables, while causations determine whether one variable causes another. causes another variable. So fundamentally, the way we look the group and I apply correlation. So that way we are saying that smoking with the lung cancer. So perfect example that we can look more about the lung cancer been done or been smoking is this the reason for lung cancer or not. So smoking is a causal factors to explore uh, for the lung cancer. So in that context, I would not say that correlation coefficient is a very much good example. So that could be done as a causality relations or statistical. But in case of the height and weight, because height and weight, both of them are going together. So you can't decide that height is cultivating or promoting weight or weight or it is other way around. So if you are not clear much about that, one thing is a causality with another or not, then correlations coefficients is suitable to apply over there. Okay. Do I need to pause for some times or anybody having any questions or I can continue at the end of my presentation we can discuss or raise some point. Mr. Amit, do I need to stop and hold and ask some questions or it could be done? End of my presentation.
No, sir, no problem. Please proceed.
Okay, that's fine.
We discussed the queries at the end of the session, sir. If you receive
I
the
see.
query.
Okay, thanks. Okay, that's fine. So example of correlations and causation, let's say we observe a strong positive correlation between ice creams and cells and drowning death does not mean that eating ice cream causes the death. Of course not. In case of the correlation is likely due to the third variable that is a warm weather. So warm weather people will eat more ice creams and swimming, which increase the risk of drowning death. So therefore, it is important to cautious when interpret the correlation and use the additional evidence to determine the causations. This is a fundamental table people mostly use, but there is not any theoretical, I would say that theoretical justification to say it. What is that? Or thresholding just correlations coefficients, but it would make sense that if it is strong negative, then the correlations coefficient is strong negative, then it should stand between -1 to -7.7, and very it interpreting as a very high inverse correlations. For example, height 0.7 to -0.3. Moderate negative, it should be if it is a moderately negative, then it should be between minus 0.3 to minus 0.1. If it is a weak negative, then it should be minus 0.0 minus 0.1 to minus 0.1. If it is a low correlations, then it should be 0 and like that. So thresholding can be done based on these different correlations coefficients. Yeah. So example correlation time series data can be also used. Correlation can be used to analyze time series data. It can be used to data that collected over time, such as stock price or daily temperature reading. Autocorrelations is a type of correlation that measures the relationship between variable with its own variable. Let's say height. A simple example is temperature. Temperature is a continuous variable. Today's temperature, tomorrow's temperature, yesterday's temperature. So if you want to see the relations between yesterday's temperature is today's temperature, that relation some extent help us to predict the tomorrow's temperature. So if you want to make the correlations between the same parameters, but they are different in respect to the time. So we can make like we can present the data like say day 0 temperature, day 1 temperature, and again put that day 1 temperature here under the column called day 0 temperature, and then put day 2 temperature here. And then again next row we can put the day 2 temperature below the day 1 temperature here, and here day 3 temperature. So basically sorry, one, each and every row will make this to make that every day temperature, that day temperature with, yeah, earlier day temperature. If we make the column, data column in such a way and make the correlations coefficients between these two parameters, then it called as a time series context correlations, and basically the auto correlations. It quite used in time series context. Not only two parameters, multiple parameters also being explored while we are working with uh, time series context by correlations coefficients, but it is also an extension of that correlation that is called auto regressions, but it is an extension of the auto correlations, auto regression. But yeah, auto correlations is basically uh, um, exploring the relation between the same variable but differing in different time points. That's the thing. Let's say we are having the daily temperature for city over the course of a year. We observe a strong positive correlations. Auto correlation indicated the temperature on a day are strongly related to the temperature of the previous day. This info can be used to picture the predict the temperature for the past day, future day based on the past previous data. Um, let's say we want to analyze the relationship between the air pollution level and respiratory disease incidence over time. We collect daily air pollution data and daily respiratory disease incident data for city over the course of year. We observe strong positive correlations between air pollution level and respiratory disease incidence, indicating that high level of air pollution are linked or associated with this increased incidence of that respiratory disease. So that is a cross correlations example. Now, once you are having that, I mentioned that once you are having this different time points, same covariate, same variables, observations, correlations, coefficients, then the correlation matrix can be formed, and it's a complex relations or so many relations between the variable over the time point. So it then it forms as matrix. So let's say in fundamentally, if you have look at the matrix like um, column is stand from column 1 to 10 from left to right, and then row from 1 to 10 from top to bottom. So 10 by 10 matrix, so let's say 100 cells being accommodated in a 10 by 10 matrix. In that 10 by 10 matrix, if we put the 10 parameters or 10 features from each row or each column, so left to right, so let's say age, then let's say height, then weight, then all the stuffs are put from left to right, whereas from top to bottom the same parameters are listed from age, height, weight, from top to bottom. Then we will see the age with age relation would be 1, perfectly they are correlated. Height with height would be 1, they will be perfectly correlated. Weight with weight will be 1, with perfectly correlated. But age with height would be something, let's say 0.8 or zero point 0.9. Age with weight, age with height, then age with weight, and age with other parameter. So this will form a typically a 10 by 10 matrix, and that 10 by 10 matrix would give you this holistic approach of the correlation between n number of parameters in a data set. So typically this correlation matrix, we use this in while you are working with the genomics data, pathway analysis, even socio-demographic relations, establishing, exploring socio-demographic relation also, we do use, we prepare the correlation matrix that is quite easy, handy to understand the data structure, is stable and display the correlation between the multiple parameters. It is useful to analyze complex data sets with multiple variable. Each cell in the matrix displays the correlations coefficients between the two parameters. So corresponding to the parameters being listed in this column wise in top row, as I mentioned, age, then height, weight, and all. And again, from top to bottom, age, again, also height, weight, and all this. So one relations can be established by correlations matrix. Let's say we want to analyze the relationship between height and weight and BMI, same sample of individual. We collected the individual's data for 100 individuals to create the correlations matrix. The matrix shows the higher height and weight have strong positive correlations, while BMI has moderate positive correlation with the height and weight. So correlations and regressions are always, so that is that correlation matrix. Now let's say about the correlations and with the regression terminology. Correlations and regressions are often used together. I would say that for the regression analysis, one of the byproduct is the correlations, but they are not same thing. Correlation measures the strength of the direction of the relationship between the two variables, whereas regressions analysis measures the relationship between the dependent variable with independent variable. It allows for the prediction of the dependent variable based on the independent variable. So if you want to explore the causal relations between the two variables, then definitely regression is much more useful than correlations and experiments. Let's use the same bill data in the previous example, but this time we want to provide the BMI based on the height and weight. We use a regression analysis to create a model that predict BMI based on height and weight. The model shows that both height and weight are significantly predict for BMI and allow us to make prediction about the BMI based on height and weight. To explore that two relationship between the two variables, typically the continuous variable, scatter plot graphical explanation is much more useful. It's graphical representation represent the relationship between two variables. They are useful for visualizing the strength and direction of the relationship between two variables. In scatter plot, each data point represents a pair of values for the two variables being analyzed. Let's use some data, the previous example, but the time we create the scatter plot of height and weight. Scatter plot shows a strong positive relationship between height and weight, with taller individually generally weighting more. Another important thing that outlier is one of the issues. So once you let's say we are having 100 individuals with height and 100 individuals with weight, and out of that suddenly we observe that one individual's height been measured as inches, but it is measured at 1000 inches. So obviously that is wrong. So that could help us, that is required to find out. And that is called the outlier detections. An outlier data point significantly different from the rest of the data. And if one individual has a huge value or outlier, obviously data correlations coefficients matrix is going to bother very much, and that need to be tackled properly. So it is going to be impact on the correlations coefficient and the statistical measure important to identify, and then other outlier appropriate statistical analysis tool need to be there. That I mentioned already, example, handling the outlier. There are several ways to handling the outlier out there. So the best process is to remove the parameters outlier from the data using that some robust statistical methods. So we can go more into details about the outlier detections, and but fundamentally there are different statistical tools are available to detect the outlier and remove those outlier. But yeah, so in principle, we should remove the outlier that makes much more noise in the data, and carry out the analysis with other values or variables values. Don't consider that the outlier variable values uh, for the analysis of the correlations coefficients. Missing data, as I already explained, like with the example of 10 and 15 individuals missing height and weight values, in that context, definitely missing data makes much more impact on the data's correlations coefficients to identify, can also significantly impact the statistical analysis, can be lead to bias estimate. It can reduce the statistical power as well, because once you reduce this 15 and 10, that is 25 individual from the data sets, so obviously your statistical power it is going to be bothered, and it makes more impact on that. It is important to handle missing data appropriately in statistical analysis. There are several methods for methods to handling the missing data, including removing case with missing data, do some data imputation technique in big data set, in primary care data. We are now working. Most cases, we don't remove the data. We do some imputation technique and quite statistical intercept techniques, but it helps us lots to retain the samples, retain the same sample size. But yeah, for some justification assumptions are required, but yeah, there is a process to handling the missing data over there. So I'd like to come to the conclusions. Conclusions is that it's useful, correlations coefficient is useful statistical method for data analysis and make the relationship between two or more variable in medical research. It can be used to identify risk factor for disease, predict disease outcome, evaluate the effectiveness of the treatment, assess the reliability of diagnostic tests, and investigate the relationship between the environmental factor and the health outcome. It is important to use correlations appropriately and to consider risk limitations and potential confounding variable when used in conjunction with other statistical methods. Correlations can be used as a valuable insight in medical research. There are some reference book, Altland, James Altman book. It's a so quite that and there are some history of correlations biometrics. So it is quite an old paper, but still you can have a look. Ruther's KG Greenstand and ALHT, they are having a modern epidemiology book that also makes, and there are some Google you can get so many things, so many correlations, coefficients on that. So thanks for listening, and if we are having any comments or query on that correlations, coefficients, or correlations, please let me know, then I can help you, try to help you at least.
Thank you, sir, for such a knowledgeable session. Now, I would like to request all participants that if there is any query regarding today's session, then please write your query in the chat box or raise your hand so I can send you the unmute request. Dr. Dharmen Kumar Pandey, please unmute yourself. Yes, yes, sir. Please.
Hello, Atanu sir. Are you
I
listening
can
me?
hear you.
Yes, sir. Sir, please explain once again the confounding variables. What are confounding variables?
See, confounding variables, it's a variable that stand along with your two parameter that you are going to explore. For example, that I gave that ice cream with that drowning death. So people take much more ice cream in that due to the warm weathers, and in warm weathers people also die uh, during swimming or drowning. Death happen.
Yes,
So
sir.
now, if you typically try to make the relations between uh, ice cream consumptions in a market and try to find out that number of death happen by make the correlation, so obviously you will find that in typically when people are taking much more ice cream, that time people are dying more. Okay, so
Yes, sir.
what does it mean? It means that people, if you eat ice cream, you will die. That kind of things are coming out. But in principle, that's not really the reason. The real reason is that the warm weather. So once the warm weather is warm, people take much more ice cream. That is a normal tendency. And people also warm weather. People also go for swimming and drownings, death and death related to this warm weathers keep on happening. So warm weather is the fundamental reasons and for two things been happen. But if you numerically, if you try to make the relations between, try to establish the relations between ice cream with the date, you will get they are quite correlations coefficients is high. But in fact, the third third variable, weather is that called confounding factor here. Similarly, you can see that people are having in fundamental epidemiology, people give much more example with this cigarette consumptions and heart attack and you know that cholesterol, let's say alcohol and alcohol taking with, let's say, heart attack.
Yes, sir.
So you're taking with heart attack. So yeah, so that's a relevant. Some people give example on that. So one thing is that obviously there is a good impact of that. If person take alcohol, then people will be having heart attack. I'm not denying it, but uh, as compared to the alcohol, cigarette is having much more impact towards heart attack. That is, it's already been proven. So, but thing is that once people take that alcohol, there is a common tendency to take that uh, smoking also. So people you will get people don't smoke and only take alcohol. People mostly take alcohol along with the smoke. So in that sense, the alcohol get much more, penalized to be measured that it is having impact on that heart attack. We are not denying, but
Yes,
alcohol having less impact on the heart attack as compared to the cigarette, because people take cigarette along with alcohol and thereafter heart attack happen. So alcohol is making here uh, relation between alcohol and death, heart attack is correlated, but leading role is taken by the so is what is it for.
hello.
Yes.
Yeah.
Yes, please.
Okay, thank you, sir. I think I solved my query.
Thank you. Thank you. Thank you, Dr. Dharmen Kumar Pandey. If there is any query, then please, we are waiting just for 1 minute. If there is any query from regarding today's session, then please write your query either in chat box or raise your hand simply so I can send you the unmute request. I have written one mail ID in the chat box. If there is any remaining query, then please mail us on the given mail ID with the subject line of the today's session. So I can forward that query to our respected sir. Thank you, sir, for very interactive and informative session. I hope that all participants get benefited from today's session. Now, on the behalf of Institute of Applied Statistics and National Institute of Ayurveda, Jaipur, we convey our sincere thanks to all the participants for their active participation and commitment for today's session. We heartily thanks the guest speaker of the session, Dr. Atanu sir, who kept participants engaged by the way of very informative session. We thanks again to all dignitaries presented in today's session. Now this is the end of today's session. We again thanks to all of you. Tomorrow we have one more session on inferential statistics testing of relationship parametric test that will be delivered by Dr. Anup Kumar sir from CPJ Lucknow. Thank you again, sir, for your valuable time and describing precisely the lecture. Again, thanks you. Thank you. This is the end of today's session.